Welcome back to the course Collaborative Robots Theory and Practice, Lecture 5, that is Inverse Kinematics of 7 Degrees of Freedom, KUKA LBR IVA Robot and Null Space. So in this lecture, we'll discuss a numerical method to do inverse kinematics. We'll see what is Newton-Raphson's method and how that can be used to do inverse kinematics of 7 degrees of freedom robot. We'll see numerical inverse kinematics algorithm to do position inverse kinematics by an example 1, that is KUKA LBR IVA 14 R820 cobot for position inverse kinematics. We'll see inverse kinematics algorithm for pose analysis. Pose here I mean position and orientation, and I'll demonstrate using example 2, that is KUKA LBR IVA 14 R820 cobot for pose analysis. Null space in cobots, what is that? I'll demonstrate using example 3, KUKA LBR IVA robot again for pose analysis with null space. So let us begin. Numerical inverse kinematics, why we should go for it? Why this is an iterative approach? Why one should choose an iterative approach to do inverse kinematics? This is very useful when analytical inverse kinematic solution is not possible. The closed form analytical solution that I have demonstrated in my previous lectures, we did that for UR5E arm, but the same is not possible if the degrees of freedom of robot is more than 6. So in that case, analytical inverse kinematic solution is not possible. To validate or improve the accuracy of analytical solution, sometimes analytical solution don't lead to very accurate solution. In those cases, in inverse kinematics using iterative approach can take it further to much closer to the desired pose that we want. Okay, so for that, and for robots with degrees of freedom of the joint space is greater than degrees of freedom in the task space, as in case of KUKA LBR IVA robot, that is the 7 degrees of freedom robot. So we'll use that to demonstrate all the algorithms that I am going to cover in this lecture. Okay, so let us have a quick recap on Newton's Raphson method. So this is a mathematical fundamental to understand this algorithm. This is an iterative numerical algorithm for finding the roots of a real valued function. Let us take a equation which needs to be solved like g theta is equal to 0, and I assume it is differentiable function in real input and real output. Initial guess, let us say if it is theta 0 or a nearby known solution is theta 0. So these are the conditions to begin Newton's Raphson's approach. Okay, so using Taylor's expansion, I can write g theta with theta 0, that is the initial guess, as this. This can be expanded like this. So g theta is equal to g theta 0 plus derivative of g theta at theta 0, and this is the theta minus theta 0 plus higher order terms are there. Okay, so keeping only the first order term and setting the g theta is equal to 0 and solving for theta to obtain this. So we can write the same equation here. We wrote g theta is equal to 0 and this can be obtained. So now using this value of theta as new guess, every time I obtain theta using this, I substitute that once again to the equation and obtain the next value of theta. Okay, so this is the procedure how the algorithm iterates. So using this value of theta as new guess for the solution and repeating equation 2 that we have seen here, this equation, okay, will get this following. Okay, so in this case theta k plus 1, the new value of theta again based on the previous value of theta, will keep on moving towards the solution. The stopping criteria here would be the difference between the previous theta and the new theta. If it goes below certain value, that is the stopping threshold that is decided before you begin the iteration. Okay, so if that goes much below the required value, so you stop the algorithm, otherwise it will keep on iterating and keep on improving that. This may be extended for a multi-dimensional real valued function for Rn as input and Rm as output. In that case, the same equation 2 can be written as this. So let us see the numerical inverse kinematics algorithm for desired position vector only. Okay, I assume x is equal to f theta is the current position, x is the current position, where theta is the vector of n joint coordinates for the given or for the current position. So f is a real valued function, Rn and Rm is differentiable, m is equal to 2 or 3 depending on 2-dimensional or 3-dimensional space we are solving for. Okay, so if it is a planar robot, it becomes 2, and if it is a 3-dimensional robot, it is 3. So this is for position vector only, so it is 3. So m is equal to 3, n is the degrees of freedom of the robot. So number of joint angles, that will be n. Okay, so let the desired end effector position be xd. This is what is the input to the inverse kinematics algorithm. This is where I want to go, and I want to find out the joint angle. Okay, so for Newton's-Raphson's method, I have written this equation with desired one as g theta is equal to xd minus fxd, and that should be equal to 0. Okay, so this is my Newton-Raphson's input equation. Okay, taking the initial guess as theta 0, I assume that is the initial guess. So most of the case the robot could be straight line, it could be all angles set as 0. Let me just show you the robot here. So let us say this is my robot. So with all the angles set as 0, it should look as this. So you can start with this position or the current position. So this is KUKA-IVA robot. So you see it has 7 degrees of freedom. So this is the first degree of freedom. This is the first joint angle I am moving. This is second one. Okay, this is third one. This is fourth one. Okay, this is fifth. This is sixth, and finally you see this is 7. Let me bring it forward. So this is your 7th joint. So you see this is your KUKA-IVA robot. So usually the current joint position is given as input, so that going from the current position to the next position is very less of a distance, and that becomes more less computationally expensive, and it takes less amount of time to calculate also. So instead of starting from all 0 position, every time the next position going to the next position would be too much time consuming also. So this can be expressed as Taylor expansion like this. I have just followed the previous equation. So xd is equal to f theta d, and that is equal to f theta 0 plus derivative this and the delta theta, that is desired from the initial guess. Okay, initial guess comes here, so that is the delta theta. Again higher order terms will come here, that I will neglect. Okay, where Jp, what is Jp? It is the Jacobian evaluated at theta 0. If you remember what was Jacobian, it is exactly this term. Okay, it is the del f theta by del theta. So this actually is equal to Jacobian of the robot. So that is evaluated at theta is equal to theta 0. Okay, so in this case it is position Jacobian. Okay, so how this Newton-Raphson's approach work? You see, you have xd minus f theta, that is plotted here, let's say, and this is your theta. So for every value starting from theta 0, you start here, you go back, project it to the curve which is here. So slope of that is something like this. So it cuts the, and it gives you theta 1 over here. This is your delta theta. From there you calculate the new value of this. So xd minus f theta 0. So you see it has moved. So again it will be projected back onto the curve. Okay, you again from here you take the slope. Okay, you will reach somewhere over here. Okay, and again you project back, calculate the xd minus f theta 1. Okay, and that is how you keep on moving theta 1. So it is now theta 2. Next theta 2 is calculated. So that way it keeps on moving till it reaches to theta d, that is the desired one. Okay, and finally you use theta d to get the actual position, that is what was desired. So now moving ahead with this equation, truncating the Taylor series at first order term only. So I have neglected the higher order terms. We can approximate this equation to this. So xd minus x is equal to jp, that is the Jacobian for position, and delta theta is theta d minus theta current. So same for the Cartesian position also. So this equation we all know very well. Okay, delta theta is equal to jp inverse ep, that is error in position. Okay, this is what I call it as error in position. We are already very familiar with this equation, as because this is the definition of Jacobian also, you can directly get to this equation. Okay, so using this, for n greater than m, that is number of degrees of freedom of the robot at the input joint space is greater than Cartesian space that it can attain. In case of two-dimensional robot it is 2, in case of 3D robot for pose analysis it is 6, for position only it is 3. So and jp becomes non-invertible. So if n is greater than m, it becomes non-invertible. So equation 6 this equation can still be solved for delta theta by replacing jp inverse with Murray-Penrose pseudo inverse that we have already established it earlier. Okay, so that is like this. So delta theta is equal to, so instead of jp inverse I can write it as jp dagger, that is equal to Murray-Penrose pseudo inverse, and equation remains the same, only the jp inverse term is now calculated differently. Okay, so now equation 8 suggests the Newton-Raphson iterative algorithm for finding theta d as this. So this time you have theta I plus 1 is equal to theta I. So this is the way it will keep on improving upon the new value of theta for the given input x. Okay, EP is the error in position and this is your pseudo inverse. Got it? Okay, so the numerical algorithm for this would be for position only. So you see what we have done here. So I have just extracted the value of Cartesian position using the transformation matrix, homogeneous transformation matrix. I have just calculated. So because you are inputting you already know the initial guess position. So you have already put the current joint position vector. So using that, do the forward kinematics, obtain the STM. From STM you can directly obtain the value of end effector position, that is the current position. Okay, so EP, that is the error is calculated as xd minus x starting from initial value I is equal to 0, and every time you keep on iterating till the value reaches very near to the actual value. So this is EP. So magnitude of EP, error in position, becomes very near to the desired value. So in that case you have to stop this iteration. So you keep on moving, use the equation as we have done here. I have used this equation again. So that comes here, and you keep on increasing next value of theta like this, and every time you calculate the new value of x. So this was the starting value of x, new value of x, and calculate the error, Cartesian error, increase I, and keep doing this whole loop till error becomes very less. Okay. So that is also position error tolerance that is set as an input before we begin this iteration. Okay. So at the end, when this whole converges and we obtain the solution, theta d desired value is obtained, okay, and that is stored here. This is what this function is going to return. Okay. So here is the example 1 when I have demonstrated KUKA LBR IVA robot, 14 kg payload and reach is 820. It is a cobot for position vector only. So I have done only position analysis. So I will be using this algorithm which is here. Okay. So in this case, desired end effector position, this is the input, this is what I want, and I want to find out the joint angles. For that I have started from initial position when all the joint angles are 0. I showed you it is vertically up, exactly straight. Okay. So this is the stopping criteria when error I want not more than 10 to the power minus 3. So in joint space degrees of freedom, n is equal to 7. For KUKA IVA it is 7 degree of freedom robot, and because I am doing only position analysis, so it is in 3D position vector, m is equal to 3. So Jacobian in this case would be 3 cross 7. So the algorithm progresses, it is illustrated here in the table. So I started with this, okay. I obtained the value of x, calculated the error, again I have moved ahead, okay. The new value of theta k will be calculated. If you look carefully here, so every time you have reached to a place, the next value of theta k will be calculated using this equation, and this is what is followed here. So new value of theta 1 is calculated using theta 0 and new value of x is there. So calculated the error, current and the desired. Okay. So you need to keep on calculating the error. So it keeps on moving and ultimately after 11 iterations it finally converges to the desired value of x. Okay. Error was 5.827 into 10 to the power minus 6. So this is the point when it should stop, because it is much below the expected error which I have set as threshold to for this algorithm to stop, and it has, you see, it has almost reached, it has reached to the desired position. Okay. So this is how it progresses. Okay. So this is my solution for all the 7 degree of freedom, all the 7 joint angles are like this. Okay. For the given position of the robot as this. Okay. Intuitively, the desired end effector position with different orientation can also be achieved. You know, this is a redundant robot, so it has multiple solutions. Okay, can also be achieved by putting theta 4 is equal to 90 degree while keeping all the remaining joints at the home position. So we just change one of the angle and it reaches here. Because I had the data sheet, I know by I can just bend one of the joint angle theta 4 by 90 degree and I can reach to this position. So it is x, this is y, this is z, and orientation is something like this. So I am not bothered about orientation here. So the algorithm takes me to this, and this is the intuitive solution, and you see in both the cases the orientations are different. So this matrix is different. Okay. So this is how, so this is my intuitive solution, just one of the angle is set to 90 degree, and this is the solution which is obtained by iterative approach. Although the end effector achieved the desired position, the orientation is different in both the cases. Okay. Hence, this algorithm is limited to inverse position kinematics only and do not have any provision for orientation inputs. Okay. So now let us look at the algorithm which does it. So for desired pose, that is position and orientation. This time the forward kinematics, I will be using both the position and the orientation. Okay, this is R is a 3 cross 3. submatrix inside transformation matrix, homogeneous transformation matrix, which gives you the sense of rotation. Okay. So, where theta is the vector of n joint coordinates. Okay. So, the given or the desired end effector pose is this. This is where I want to go, TD. Okay. So, this again will have x desired and r desired, position and orientation. This is where I want to go. Okay. This is the current one. Okay. So, initial guess, I start with theta 0. In robotics, it is usually the current position vector, not all straight. From straight, if you start all 0, it takes too much of time to converge. So, I start with where I am to the next point, next point. So, iteratively you can even feed the trajectory, current position to next position, next position, next position, and the robot keeps on going using inverse kinematics. Okay. So, this is my initial guess. So, extracted desired end effector position vector from homogeneous transformation matrix, this is HTM. Okay. So, I can take it from the transformation matrix. So, XD is this, and end effector orientation matrix, again it is a sub matrix from homogeneous transformation matrix, this one is here. So, the position error vector EP and the orientation error vector E omega would be combined together now. So, E, that is the error vector, will have E omega and EP both. Okay. So, it is written as this. So, now end effector position error vector is quite trivial, it is very easy, similar to the earlier algorithm. So, error vector is simply xd minus x, that is the error vector for position. So, end effector orientation error vector would be, let RE be the required orientation to make end effector achieve the desired orientation from the current orientation R. So, mathematically RE, so this is a rotation matrix which when applied to the current orientation R gives you RD, desired orientation. Okay. So, this is basically the orientation RE. So, whole of the R, sense of R remains with RE. So, RE is RD and R transpose. I have used the property R inverse is R transpose. Okay. So, that is what I have put here. You see, you are basically rotating about an axis something like this, so that your current orientation from here goes to a new location. Okay. So, you have rotated about some angle, so that rotation matrix is your RE. Okay, RE. So, you were, this has the sense of current R, and finally you reach till R desired. Okay. So, R to R desired, you rotated about an axis using RE and you reached till there. Okay. So, this is a geometrical sense of this, but that is not so trivial here. Okay. So, now RE can be expressed as, it is rotated about an axis R by an angle phi as this. So, this you remember, this is a general rotation matrix about an axis is given by R is this. This we have derived it earlier also. Okay. So, V phi is versine phi and it is 1 minus cos phi. Okay. So, this is it. So, RE can be written like this. So, now moving ahead. So, the given rotation, you know the inverse solution for this also. So, given the rotation matrix RE, if this is already given and that is equivalent to this, we know here the inverse problem to compute the axis R and angle phi is this. So, phi is given by this, R can be evaluated like this. Okay. This is, we have done it earlier. So, it is exactly the same. So, R is equal to 1 by 2 sin phi is, using the elements of this matrix you can obtain this. Okay. So, now I am rearranging this. So, as to make it very convenient to use it further in our algorithm. So, R sin phi is equal to, this is what is here. So r sin phi, okay, r is having components of rx, ry and rz, and that becomes equal to 1 by 2 of this, and this has the sense of e omega error, orientation error, as I have shown it here also. So you have a axis r about which you are rotating by an angle phi, this is r. So you started with here, okay, and you reached till here. So you started, this is your current, and you did something Re, and finally you reached till R desired. Okay, so this is how it is happening. Okay, so this is your E omega. So E omega extracted out of this has a sense of error in omega, which actually takes you from R to Rd. Okay, this is what we have calculated here also. So the orientation error vector may now be written as E omega is equivalent to R sin phi, because you know phi, reducing the phi, if Newton-Raphson scheme will keep on reducing the phi, ultimately E omega will be reduced. Okay, so that error is reduced. This is what is the orientation error vector. Okay, so now let Rd is equal to this and R is equal to this. N is normal, orthogonal and approach vectors, you know this. So any rotation matrix will have this form, N, O and A clubbed together. So for Rd and R, I have kept it like this. Rd is the desired one, R is the current one. So if I use this Rd R transpose and do this calculation, I get to this directly. Now subtracting the elements 2, 3 from the element 3, 2. Why I did it? You just check this equation, 3, 2 and 2, 3. Similarly 1, 3 and 3, 1, 2, 1 and 1, 2. So that I can calculate exactly Rx sin phi, Ry sin phi, Rz sin phi. Okay, and 1 by 2 will come to this side. So if I do that, I can directly get 2 times of Rx sin phi, 2 times of Ry sin phi, 2 times of Rz sin phi, and I can quickly obtain this. Okay, so again by rearranging the above three expressions using vector matrix forms of R and Rd, it gives me this. You can do this exercise of your own. So it is exactly using the matrices also you can obtain this. You can do this and you can directly obtain this. So this is what will directly give you R sin phi. Okay, this is all in vector. So similar to equation 8, you see you have delta theta is equal to J inverse at theta 0, evaluated at theta 0, and this is error. Error here is composition of E omega and E position. So both of them are clubbed together. Okay, so J theta 0 is the body Jacobian evaluated at theta 0, and J inverse is a Murray-Penrose pseudo inverse of J, that is evaluated like this because it is m cross n. Okay, so using equation 14, the Newton-Raphson iterative algorithm for finding theta d would be this. Okay, so you keep on calculating next value of theta using the previous one and Jacobian inverse of error. Okay, so this becomes my new equation. Okay, I will use this and do this calculations. It is exactly similar to the previous one, but in this case you also have E omega because you are doing both position and orientation analysis. Okay, so desired end effector pose is given, that is input to this inverse kinematics algorithm. Current joint position vector or 0, 0, 0 position, end effector position tolerance where you want to stop your algorithm. This is tolerance in terms of orientation. Okay, so both the inputs should be there. Yes, so you have again extracted x and xd and calculated EP directly, and calculating E omega I have used this equation, this one. Okay, and that equation comes directly here. E omega is calculated like this. Okay, and total error will be composed of E omega and EP, transpose of that. Cp is the cross product that is used here. So I will return the error finally, so that what is my error I will come to know also. That becomes the stopping criteria also for this. So end function. So this is the evaluating the error function, okay, and that will be used here. This error function is used here. This is the numerical inverse kinematics algorithm for position and orientation. In this case, error is calculated starting from I is equal to 0. Now the actual iteration begins with the threshold. Okay, so as long as the error comes down below E omega and EP, okay, so T epsilon omega and epsilon p, I will keep on moving it. Okay, E is the error. So new value of thetas are calculated. You set the new value of theta then to the previous value, update with the new value of theta and calculate the HTM, homogeneous transformation matrix, calculate the error again and increase the value of I by 1 and keep on doing this iteration till the thresholds are achieved, and finally you return theta d. Okay, theta d, that is the desired theta d, you reach till there. Okay, so I have again used this algorithm to do inverse kinematics analysis of KUKA-AIVA robot for position and orientation. I have assumed it is initially at home position, all 0 0 0. So that is the reason current joint position is taken as 0. Okay, TD is equal to, this is what I desire, the end effector position and orientation. Okay, so these are the thresholds where I want the algorithm to stop iterating. Okay, 10 to the power minus 3, 10 to the power minus 3 in both position and orientation. Units are, corresponding units are taken. Joint space degrees of freedom is 7, task space is 6. So that is the reason J theta would be 6 cross 7. Okay, so you see I have again started with 0 0 0 and I have kept on updating the new values of theta to this. So it took total of 17 iterations to converge to the solution, and finally the threshold in error has achieved and I got the final theta d desired value. Okay, so this is where I wanted to go, and this gives me directly. So this can be verified using forward kinematics. If you put that, do forward kinematics, you should be getting the input homogeneous transformation matrix. So both are same in my case. So I got the desired pose which is achieved. So it looks like this. Okay, any random test you can do, not just this one. Let us discuss what is null space. This is quite common in case of redundant robot, as in case of KUKA-AIVA. You have seen number of angles, joint angles are 7, whereas the output you can only obtain 6 parameters, that is x, y, z and roll pitch yaw of the end effector. So 6 in the output, 7 in the input. So your Jacobian was no longer a square matrix. So in those cases, mathematically, let us have a quick recap of what is null space. So let A be a real valued matrix, okay, of m cross n, where n is greater than m. In our case it was n for degrees of freedom, that is 7, m was 6. It be a non-square matrix defining the system of linear equation as Ax is equal to b. Okay, so the null space Nj of A is set of all x which is when multiplied by A results to a 0 vector. So mathematically the null space of A is a set of all x, all the x which is there, which when multiplied with A results to a 0 vector. So it can be given as, so null of A is x, a real valued vector, okay, and Ax is equal to 0, such that Ax is equal to 0. Okay, so in robotics you have J theta dot is equal to twist. J is the Jacobian, theta dot is the joint rate, and T is the end effector velocities, angular as well as linear velocity, that is known as twist. Okay. So this has a similar form as this one you see. So now for redundant manipulator, J is a non-square matrix. In case of KUKA-IVA robot, J is 6 cross 7. Okay. So there exists a matrix theta 0 dot. So you will have a set of theta 0 dot for which twist becomes equal to 0. So you see there is no motion at the end effector where theta 0 dot still exists, for which j theta 0 dot is equal to 0. So this means that joint space motion is not creating any motion in the task space. So in the task space you don't see any motion, but joints are moving. Okay, so that is the case. So let me show you a small video here which will clear it up very well. Okay, that experiment that I have done. So this is the video. You see the whole of the robot is moving, okay, but end effector is stationary. There is no velocity at the end effector. Okay, so this is a redundancy demonstration when you see robot is moving in the null space. For null space motion, for a kinematically redundant manipulator, a non-empty, non-null space exists which is available to set up systematic procedure for an effective handling of redundant degree of freedom. The general inverse kinematic solution now can be written using a null space like this. So this was our earlier equation. So apart from that, if we consider null space also, so this is my inverse kinematic solution. Mathematically it is there, where one vector is identity matrix of order n. The matrix 1 minus j inverse j is projector of the joint vector, okay, theta 0 dot onto the null space. Okay. The contribution of theta 0 dot is to generate null space motions of the structure that do not alter the task space configuration, but allow manipulator to reach postures that are more dexterous for execution of a given task. Okay. So this is very useful. You still have the same position and orientation, but robot can move. So that may be very helpful to do some kind of dexterous manipulation, as in case we want to pick up something from within a jar and the jar mouth is actually obstructing it. So you can have multiple orientation combination to actually get into the jar without directly obtaining to the object which is inside the jar. Okay, without directly obtaining it, you go from the top and get in. So that is basically giving you a sense of collision free path or maybe those kind of things. So typically the choice of null space velocity vector is given by this. So this is your theta 0 dot, that is what was used here. Okay, so this theta 0 dot is given as alpha times of del w by del theta, where alpha is a number greater than 0 and w theta is a scalar objective function of the joint variables, and del omega by del theta is a vector function representing the gradient of w. So it is sought to locally optimize w in accordance with kinematic constraints by the above equation. So based on different types of kinematic constraints, you can define theta 0 dot using this equation. So let us see what could be the multiple objective functions. Okay, usually the objective functions are manipulability measure as defined by j transpose square root. So this is what, this is a determinant of j transpose, which is a number taking the square root. It is defined by the manipulability measure that we have seen earlier, which vanishes at a singular configuration, and thus redundancy may be exploited to escape singularities. So you see the function w can now be used to escape the singularities. If at all it is there in the path, if it is coming, so you can use this function to define your theta 0 dot, so as to define your robot's inverse kinematic solution, and finally it escapes the singularity. So this is one of the way to escape from singularity. The next function could be a distance from mechanical joint limits. So a robot joint always has some limits, so it cannot go below this and above this, okay, and it should operate within this range. So I want to be somewhere in between all the time. My solution, I want, even though it has infinite solution in between, but I want to be somewhere in between this, so as to avoid any joint limiting, okay. And the distance from mechanical joint limit is defined as this: w theta is equal to minus 1 by 2n, n being the degrees of freedom, summation of this, okay, where theta I m denotes the maximum, inside one is the minimum limit of theta I bar is the middle of the joint range, so it is somewhere here, okay, middle of the joint range, okay. So that is used here. So using that, it is defined as this. So this is the function making it go some within the joint limits, and thus redundancy may be exploited now to keep the manipulator off the joint limits, okay. So again there is another type of function which may be used. This is distance from the obstacle, where O vector here is the position vector of opportune point on the obstacle, and P theta is the position vector of the closest manipulator point to the obstacle, and thus redundancy may now be exploited to avoid collision with any obstacle on the way, okay. This is an external obstacle I am talking about, okay. So these are few functions which can be used. So let us use one of them. So as you have seen, the null space motion to avoid mechanical joint limit is defined as this. So it is defined as this, okay. So if I expand this summation, it brings you to this, and taking partial derivative of this, I can create now the vector of del w by del theta 1, theta 2, theta 3, like that. So this is your calculation for that. So individual partial derivatives are written here, okay. So if I pack them together, I create the vector form, it will result in this. So this I have expressed as one can use directly in MATLAB. So dot slash means element wise division, so the vector can be expressed like this, and similarly del w by del theta can now be written. So now this is in vector form. Dot square 2 means element wise square, okay. So then theta 0 dot is equal to alpha times of del w by del theta, that one you have calculated here, okay, that comes here. L is the scalar value. So now this can be written as this. So this is compatible with MATLAB programming if somebody wants to do it, okay, where theta is the current joint position, theta bar is the middle of the joint range, theta m is the maximum limit, and theta small m is the joint minimum limit, okay. So using this is expressed. Now let us put this in algorithm form. So input is the end effector pose, okay, TD, okay. This is the desired pose, that is where you want to go. Current joint position vector, this is the initial guess for Newton-Raphson scheme now. End effector position error tolerance, so these are the tolerance for position and orientation which you specify for Newton-Raphson scheme to stop somewhere. Joint upper mechanical limit and lower mechanical limit to make use of this, okay. So that is what is used here, and evaluation of theta dot is done over here using this part of the algorithm. theta dot, that is calculated using this. Okay. So that is calculated here. This function will return theta 0 dot. Okay. Now the error as we have calculated earlier also, this is the way you calculate the error in position, error in omega, and pack them together, return it. Okay. So mid range is defined as theta m, capital M, small m by 2 mid, and this is the range. Okay, this is the range. These are also some of the calculations which is used for this calculation, used in this algorithm. Okay, now again starting the Newton-Raphson iteration. Okay, you keep on doing it till you achieve the error below some value. So this is for error calculation. Error you are calculating here, increasing the I, right? This is iterating with theta and calculating the new theta, new theta, new theta, and finally you reached here. Evaluate theta dot, this is from the previous function, and keep on doing iteration till you reach the threshold, and ultimately you return the desired theta. If it reaches near to the threshold of stopping criteria, you directly return the theta. Okay. So considering this problem mentioned in example 2 we did it once, okay, using pose analysis. The same one will incorporate now, and will also implement null space motion, and will exploit the joint limits now. Okay. So incorporating the joint limits provided by the manufacturer, that is KUKA in this case, to generate the inverse kinematic solution within the joint limits. So I don't want my solution to go off the joint limits. Okay. This can be achieved using null space motion by utilizing the objective function of the mechanical joint limits. Okay. So these are the values which are given by the manufacturer here. So A1, axis 1 cannot go more than plus minus 170 degree, axis 2, axis 3, 4, 5, 6 and 7. So all the motion is already given by KUKA here. So this is what is the joint angle limits which is given by KUKA LVR Aiwa manufacturer KUKA. Okay. So using algorithm 3, you see now I got theta d is this, theta 1, theta 2, theta 3, theta 4, 5, 6 and 7. All the 7 joint angles are obtained with the tolerance like this. Okay. So this is where this was the stopping value of E omega and EP, that is the offset from the desired position and orientation. This is what I got, and the algorithm stopped. Okay, this is what we get. Earlier in algorithm 2, you see you got 173, 26, 61, 73 like this, where you see theta 1, if you see the manufacturer's joint limits, it should not have gone beyond 170 degree plus or minus, right? But in this case, it is much above the 170 degree. So it has gone up to 173 degree. So example 2, which didn't use the joint angle limits in its algorithm, so it went, the solution went beyond that. But in this case, it is well within the limits. Okay. So it may be observed that all the joints are within their mechanical limits, unlike example 2, and still the end effector has achieved the desired pose. Okay. Okay, that's all for this lecture. So in the next lecture, I will start with a new module, that is robot statics. Thanks a lot.